Time does not flow the same way everywhere. It stretches, it bends, it responds to motion and gravity. Tonight we will move through something that seems steady and familiar, and discover that it is neither steady nor universal. As you lie still, the universe is quietly adjusting the rate at which your seconds pass. So settle in. Allow your thoughts to soften. Before we begin, let me know in the comments below where you are tuning in from and what sleep science topic you'd like to hear next. I love to hear your thoughts, and engagement helps YouTube find others that will also enjoy these videos. Now, let us begin slowly with the simple idea that time itself can change. Time feels uniform because our daily lives unfold within nearly identical conditions. The clocks around you tick together. Your phone agrees with the wall clock. Morning follows night in a steady rhythm. But this apparent uniformity is local, not universal. In the broader structure of the cosmos, time does not pass at the same rate everywhere. Its flow depends on motion and gravity. Two observers in different conditions can measure different durations between the same pair of events, and both measurements can be correct. This is not a malfunction of clocks. It is not a flaw in measurement. It is a property of space-time itself. According to relativity, time is woven together with the three dimensions of space into a four-dimensional structure. When motion changes or when gravity deepens, the geometry of space-time changes as well. And when geometry changes, so does the rate at which time advances. Seconds lengthen, intervals stretch, the ticking adjusts, and yet, to each observer, time feels normal. It does not announce its flexibility. It simply carries you forward, quietly, at the rate defined by where you are and how you move. The idea that time can stretch did not arise from speculation. It emerged from a simple, stubborn fact about light. In 1905, Albert Einstein proposed that the speed of light in a vacuum, denoted by the constant CCC, must be the same for all observers, regardless of their motion. Whether you move toward a beam of light or away from it, you measure the same speed. This single constraint reshaped physics. If the speed of light cannot change, then something else must. Distances can contract, time can dilate. The variables x, x, x and t, t, t become flexible in order to preserve the invariance of CCC. This framework is known as special relativity. It does not treat time as a rigid backdrop. Instead, time becomes dynamic, linked to motion through the geometry of space-time. Later, general relativity extended this idea to gravity, showing that mass curves space-time and alters the passage of time as well. What began as a consistency requirement for light revealed something profound. Time is not absolute. It adjusts itself to preserve the deeper symmetry of the universe. Time dilation appears in two distinct but related ways. One arises from velocity, from motion through space. The other arises from gravity, from the curvature of space-time caused by mass. Though their causes differ, both forms reshape how time flows relative to different observers. Velocity-time dilation belongs to special relativity. When two observers move relative to one another, each measures the other's clock as running slower. This effect grows stronger as speeds approach the speed of light. Gravitational time dilation, described by general relativity, occurs because mass bends space-time. The stronger the gravitational field, the slower time passes relative to regions with weaker gravity. A clock closer to a massive object ticks more slowly than one farther away. These two mechanisms, motion and gravity, operate continuously throughout the universe. And even now, resting quietly on Earth, you are experiencing both. Your time is shaped by the planet beneath you and the motion carrying you through space. When an object moves quickly relative to you, its clock ticks more slowly than your own. This is not metaphorical. It is not about perception. It is a measurable consequence of motion through space-time. If two identical clocks begin synchronized and one travels at high speed before returning, it will show less elapsed time than the clock that remained at rest. Motion alters duration. The reason traces back to the invariant speed of light. Because CCC must remain constant for all observers, space-time adjusts its geometry. The The mathematical expression that describes this effect includes the Lorentz factor, which increases as velocity approaches light speed. As that factor grows, time intervals stretch. Proper time, the time measured by the moving clock itself, becomes shorter relative to the stationary frame. The faster the motion, the greater the dilation. And yet, inside the moving frame, nothing feels unusual. The traveler's heartbeat, thoughts, and breath unfold normally. Time does not feel slowed. It simply becomes different when compared later. Quietly reduced, like a path that turned out to be shorter than expected. Gravity does more than pull objects inward, it reshapes space-time itself, and when space-time curves, time flows differently within that curvature. The stronger the gravitational field, the slower time passes relative to regions of weaker gravity. A clock placed closer to a massive object will tick more slowly than one positioned farther away. This effect arises from general relativity. Mass tells space-time how to curve, and curved space-time tells matter and clocks how to move. In stronger gravitational wells, the component of space-time associated with time becomes stretched. The deeper you go into a gravitational field, the more pronounced the dilation. Even on Earth, this effect is measurable. A clock at sea level ticks slightly more slowly than one on a mountaintop. To the person standing at either location, nothing feels altered. The seconds feel steady. But from a broader view, the mountain clock advances just a little more quickly, as if the higher air allowed time to breathe more freely. Time dilation is not a theoretical curiosity. It has been measured repeatedly with extraordinary precision. Modern atomic clocks are so accurate that they can detect time differences caused by changes in speed and altitude over small distances. When physicists compare clocks that have been moved or elevated, they observe exactly the differences relativity predicts. One landmark confirmation involved flying atomic clocks aboard aircraft and comparing them to synchronized clocks on the ground. After the flights, the airborne clocks showed tiny but measurable differences in elapsed time. These variations matched the combined predictions of velocity time dilation and gravitational time dilation. Motion slowed the clocks slightly. Higher altitude with weaker gravity allowed them to tick slightly faster. These shifts are small in daily life, billionths of a second, but they accumulate, and their consistency across experiments confirms something steady and quiet. Time truly adjusts itself in response to motion and gravity, exactly as relativity describes. Motion through space and motion through time are deeply linked. In relativity, an object's movement can be understood as a trajectory through four-dimensional space-time. When more of that motion is directed through space, less remains directed through time. The result is time dilation. Increasing spatial velocity reduces the rate at which proper time accumulates. This relationship becomes dramatic at speeds approaching light. At 90% of CCC, time slows significantly compared to a stationary observer. At 99%, the effect becomes profound. The Lorentz factor grows rapidly as velocity increases, stretching time intervals more and more. Yet the speed of light itself remains unchanged. Space-time adjusts instead, preserving its internal consistency. From within the moving frame, however, life proceeds normally. Thoughts unfold. Clocks tick steadily. The slowing appears only when compared across frames. It is as if two rivers flow side by side at different rates, unaware of their difference until they meet again. Before relativity, space and time were treated as separate stages on which events occurred. Relativity revealed something subtler. Space and time are woven together into a unified structure called space-time. Events are not located only in space or only in time, but within a four-dimensional geometry that includes both. This geometry determines how distances and durations relate. The separation between events is described not simply by spatial distance or time interval alone, but by a combined quantity called the space-time interval. This interval remains invariant across observers, even when measurements of space and time differ individually. What one observer calls a longer duration and shorter distance, another may measure differently. Yet the underlying space-time interval stays constant. Space-time is not visible, but it governs every measurement you make. As you rest, you are tracing a smooth path through it, a world line extending quietly forward, carried by gravity, motion, and the steady curvature of the universe itself. It feels natural to imagine that there is a single present moment shared across the universe, a vast cosmic now unfolding everywhere at once. But relativity gently dissolves this intuition. Two observers moving relative to each other can disagree about whether distant events happened at the same time. Simultaneity is not absolute, it depends on motion. In special relativity, time and space coordinates shift between observers according to the Lorentz transformations. If you are moving relative to me, your definition of "at the same time" slices through space-time at a slightly different angle than mine. Events that appear simultaneous in one frame may occur in a different order in another. Neither observer is mistaken. Each description is internally consistent within its frame. This does not disturb your immediate experience. The room around you shares a common present because relative speeds are small, but across vast distances and high velocities, now becomes local, a quiet reminder that time is stitched into motion. When two observers move relative to one another, they will not agree on how much time passes between the same two events. This is one of the central results of special relativity. If you watch a clock traveling past you at high speed, you will measure its ticking as slower than your own. From the traveler's perspective, however, your clock appears slow instead. The difference arises from how space-time coordinates transform between inertial frames. Each observer measures time using their own proper time, the time experienced along their world line. Because their motion through space-time differs, the intervals they calculate differ as well. The Lorentz factor determines the magnitude of this dilation, growing larger as velocity increases. Importantly, neither observer experiences their own time as altered. Each feels normal within their frame. It is only when clocks are later compared, brought together after relative motion and acceleration, that the asymmetry becomes measurable. Until then, both perspectives remain valid, balanced within the geometry of space-time. At the heart of special relativity lies a single constraint. The speed of light in a vacuum, CCC, must be the same for all observers, regardless of their motion. Whether you move toward a beam of light or away from it, you measure the same value. This invariance is not optional. It is woven into Maxwell's equations and confirmed by experiment. Because CCC cannot change, the variables that describe space and time must become flexible. If distance xxxx were fixed and time ttt were fixed, observers moving relative to one another would measure different light speeds. To prevent that inconsistency, space-time reshapes itself. Distances contract along the direction of motion. Time intervals dilate. Together, these adjustments preserve the invariant speed of light. This is not a philosophical reinterpretation. It is a geometric necessity. Light holds steady, and space-time bends to accommodate it. As a result, time itself becomes responsive, not rigid, but adaptable within the deeper symmetry of the universe. Imagine a simple clock built from two mirrors facing each other, with a photon bouncing between them. Each round trip of the photon marks one tick. Inside a stationary spacecraft, the photon travels straight up and down between the mirrors. The path is vertical and the timing is steady. Now imagine the spacecraft moving at high speed relative to you. From your perspective, the photon no longer travels straight up and down. As the ship moves forward, the photon traces a diagonal path between the mirrors. That diagonal path is longer than the vertical one, yet the speed of light cannot change. Since CCC remains constant and the path length increases, the time between ticks must increase. The moving clock runs slower. This thought experiment is the gold standard for visualizing velocity-time dilation. It does not rely on intuition alone. It rests on geometry and the invariance of light speed. A longer path at the same speed requires more time, and so motion stretches the tick. At everyday speeds, cars, airplanes, even spacecraft, time dilation is extraordinarily small. The Lorentz factor remains close to 1, and the stretching of time is measured in tiny fractions of a second. But as velocity approaches the speed of light, the effect grows rapidly and non-linearly. At 90% of CCC, time slows noticeably relative to a stationary observer. At 99%, the dilation becomes far more dramatic. The mathematical expression governing this effect shows that as velocity approaches CCC, the denominator of the Lorentz factor approaches 0, causing the factor to increase sharply. Time stretches more and more with each incremental increase in speed. Yet no object with mass can reach light speed. The energy required rises without bound, so time can be slowed dramatically but never completely halted through motion alone. It stretches asymptotically, approaching stillness but never fully arriving there. Although dramatic time dilation requires extreme velocity, the effect exists at all speeds. Even walking across a room changes your motion through space-time slightly. The difference in elapsed time between two people moving at different everyday speeds is unimaginably small, far below human perception, but it is real. Atomic clocks are precise enough to detect these minute variations. When compared carefully, clocks moving at slightly different speeds diverge by fractions of a billionth of a second. These differences align perfectly with relativistic predictions. The equations do not switch on only at high speed, they apply continuously. This means that no two world lines are identical. Every motion traces a slightly different path through space-time, accumulating time at a slightly different rate. The variations are subtle, but they are universal, woven quietly into even the simplest steps you take. High above Earth, satellites orbit at thousands of kilometers per hour. Their motion produces velocity time dilation, causing their onboard clocks to tick slightly slower relative to clocks on the ground. At the same time, because they are farther from Earth's center, they experience weaker gravity, which makes their clocks tick slightly faster due to gravitational time dilation. These two effects act in opposite directions. For GPS satellites, the gravitational effect dominates, meaning their clocks run faster overall compared to clocks on Earth's surface. Engineers must account for both contributions, special and general relativity combined, when calibrating the system. If these corrections were ignored, navigation errors would accumulate rapidly. Within a single day, positional accuracy would drift by kilometers. The quiet functioning of your phone's map depends on relativistic time adjustments happening continuously above you, each satellite tracing its own slightly altered rhythm through space-time. The global positioning system relies on extraordinary timing precision. Each satellite carries atomic clocks that broadcast signals stamped with exact time readings. Your receiver calculates position by measuring how long those signals take to arrive. Even a microsecond error translates into hundreds of meters of positional drift. Because satellites move quickly and orbit in weaker gravity than Earth's surface, their clocks experience both velocity time dilation and gravitational time dilation. The net effect causes their clocks to run faster than identical clocks on Earth by about 38 microseconds per day. That number may sound small, but uncorrected, it would produce navigation errors of several kilometers daily. Engineers pre-adjust satellite clocks to compensate for these relativistic effects. The corrections are not optional refinements, they are essential. Each time you follow directions across a city, you are quietly relying on Einstein's equations, on the measured fact that time does not flow uniformly between Earth and orbit. Gravity is often described as a force pulling objects together, but in general relativity, gravity is something subtler. Mass and energy curve space-time, and objects move along the curved geometry. Planets orbit stars not because they are being tugged invisibly, but because they are following the natural contours of space-time around mass. When space-time curves, both spatial distances and time intervals are affected. The curvature alters how clocks tick. Near a massive body, the time component of space-time stretches. This stretching slows the passage of time relative to regions where space-time is less curved. The bending is invisible but measurable. It guides planets, shapes orbits, and alters the rhythm of clocks. As you rest on Earth, you are held not only by gravity's pull, but by the curvature of space-time beneath you, a gentle warping that quietly slows your seconds compared to the emptier reaches above. A clock placed at higher altitude experiences weaker gravitational pull than one at sea level. According to general relativity, weaker gravity means less curvature of space-time and therefore less gravitational time dilation. The higher clock ticks slightly faster. This effect has been measured with astonishing sensitivity. Physicists have compared atomic clocks separated by only a few centimeters in height and observed the predicted difference in ticking rates. Even the thickness of a book can create a measurable change in time's passage when the instruments are precise enough. The effect is tiny in daily life. You would never notice it while climbing a staircase, but it is real. The summit of a mountain ages ever so slightly faster than the valley below. Time breathes more freely where gravity's grip is softer. In 1959, physicists Robert Pound and Glenn Rebka conducted a landmark experiment at Harvard University. They measured the gravitational redshift of gamma rays traveling up and down a tower. According to general relativity, light climbing out of Earth's gravitational field should lose energy, stretching to slightly longer wavelengths. Because frequency and time are linked, this redshift reflects gravitational time dilation. If time flows more slowly in stronger gravity, then light emitted lower in a gravitational field will appear shifted when observed higher up. Pound and Rebka detected exactly the shift predicted by Einstein's equations. The experiment required extraordinary precision, yet its conclusion was calm and definitive. Gravity alters time. The tower itself became a quiet laboratory for curved space-time, demonstrating that even Earth's modest mass reshapes the flow of seconds. The strength of gravitational time dilation depends on mass and proximity. The closer you are to a massive object, the stronger the curvature of space-time and the slower time passes relative to distant observers. As mass increases, so does the effect. Near Earth, the difference is small. Near a neutron star, it becomes dramatic. A clock placed on the surface of a neutron star, an object with the mass of the Sun compressed into a city-sized sphere, would tick significantly slower than a clock far away. The deeper the gravitational well, the more stretched the time coordinate becomes. Yet again, locally, nothing feels unusual. An observer standing on that dense surface would experience time normally. Only when compared across distances would the difference reveal itself. Time does not announce its bending, it simply follows the curvature laid out by mass. Astronauts orbiting Earth move at high speeds relative to the planet's surface. That motion produces velocity-time dilation, slowing their onboard clocks relative to clocks on Earth. At the same time, being farther from Earth's center reduces gravitational time dilation, which would otherwise speed their clocks up. The two effects compete. For astronauts in low Earth orbit, the velocity effect dominates slightly. As a result, they age marginally slower than people on the ground. The difference is tiny, measured in milliseconds over months, but it is measurable and consistent with relativistic predictions. When they return, they are technically younger by a fraction of a second than they would have been had they stayed on Earth. It is a small gift of motion, a subtle shift in accumulated time earned simply by circling the planet at extraordinary speed. If a spacecraft were to travel at speeds close to light, the difference in elapsed time between traveler and stationary observer would grow large. At velocities like 99% of CCC, the Lorentz factor increases sharply, meaning time aboard the ship would pass much more slowly compared to Earth. For the traveler, months might pass while years unfold back home. The relationship is not linear. It accelerates as speed approaches light. The mathematics describe how proper time along the traveler's world line becomes shorter relative to coordinate time in the stationary frame. This possibility is not science fiction. It is a direct prediction of special relativity. Motion through space reshapes motion through time. The faster you travel, the less time you accumulate, a quiet exchange written into the geometry of space-time itself. When velocity reaches 90% of the speed of light, time dilation becomes substantial enough to feel mathematically dramatic, even if it remains imperceptible locally. At that speed, a factor known as the Lorentz factor rises to a little over 2. This means that for every 1 year experienced by the traveler, more than 2 years pass for someone at rest relative to that traveler. Time has not stopped, it has stretched in comparison. This effect comes from the relationship between velocity and the invariant speed of light. The stretching factor equals 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. As velocity approaches light speed, that denominator becomes smaller, causing the stretching factor to grow larger. Time must expand to preserve light's constant speed, yet inside the moving frame, life feels steady. Clocks tick normally. Breath follows breath. Only when paths reunite does the difference reveal itself. Increase the speed further to 99% of light speed and the Lorentz factor rises to about 7. For every year that passes on the spacecraft, roughly 7 years pass for an observer at rest. The relationship is non-linear. Each incremental increase in speed near CCC produces disproportionately larger dilation. The mathematics show why. As velocity approaches light speed, the denominator inside the Lorentz factor approaches zero, causing the factor to rise steeply. Yet it never becomes infinite because no object with mass can reach CCC. The required energy increases without bound. Time dilation then grows dramatically but asymptotically. The closer you move to light speed, the more stretched your time becomes relative to others, approaching stillness but never quite reaching it. The twin paradox imagines one twin traveling at high speed through space while the other remains on Earth. Upon returning, the traveling twin is younger. At first glance, the situation seems symmetrical. Each twin sees the other as moving. So which one ages less? The resolution lies in acceleration. The traveling twin must turn around to return home. That turnaround, the act of accelerating and changing inertial frames, breaks the symmetry. Without that acceleration, both twins could indefinitely claim the other's clock runs slower. But once one twin accelerates, the geometry of space-time assigns different world lines to each. The proper time accumulated along those paths differs. This is not illusion. It has been confirmed in experiments involving precise clocks flown on aircraft. Acceleration marks the divergence. One path through space-time is shorter in proper time than the other, and the clocks quietly record it. In inertial motion, constant velocity, time dilation is symmetrical. If you and I pass each other at high speed, each of us measures the other's clock as running slow. Neither perspective is privileged. Both are correct within their frames. Acceleration changes that balance. When one observer changes velocity, turning around, slowing down, or speeding up, they shift between inertial frames. This frame change alters how simultaneity is defined across space-time. Events that were once considered simultaneous are reassigned. It is this shift that resolves the apparent paradox. The act of turning around is not minor. It reshapes the traveler's path through space-time. Once reunited, the clocks can be directly compared, and the asymmetry becomes measurable. Acceleration is the hinge on which time's symmetry pivots. Here is one of relativity's most subtle truths. If you and I move past one another at 0.9 c, I observe your clock ticking slower than mine. At the same time, you observe my clock ticking slower than yours. Both observations are valid. Neither of us is wrong. This symmetry arises because time dilation depends only on relative velocity. In each inertial frame, the other is moving. The Lorentz transformations preserve consistency. The brain melter quality of this fact comes from our classical intuition, which expects one clock to be truly slower. Relativity replaces that expectation with geometric consistency. The paradox dissolves only when one observer accelerates and the two frames are reunited. Until then, both clocks appear slow from the other's perspective. Two drifting rivers, each seeing the other flow more gently until one curves back to meet the shore. When velocity reaches 90% of the speed of light, time dilation becomes substantial enough to feel mathematically dramatic, even if it remains imperceptible locally. At that speed, a factor known as the Lorentz factor rises to a little over 2. This means that for every 1 year experienced by the traveler, more than 2 years pass for someone at rest relative to that traveler. Time has not stopped, it has stretched in comparison. This effect comes from the relationship between velocity and the invariant speed of light. The stretching factor equals 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. As velocity approaches light speed, that denominator becomes smaller, causing the stretching factor to grow larger. Time must expand to preserve light's constant speed, yet inside the moving frame, life feels steady. Clocks tick normally. Breath follows breath. Only when paths reunite does the difference reveal itself. Increase the speed further to 99% of light speed and the Lorentz factor rises to about 7. For every year that passes on the spacecraft, roughly 7 years pass for an observer at rest. The relationship is non-linear. Each incremental increase in speed near CCC produces disproportionately larger dilation. The mathematics show why. As velocity approaches light speed, the denominator inside the Lorentz factor approaches zero, causing the factor to rise steeply. Yet it never becomes infinite because no object with mass can reach CCC. The required energy increases without bound. Time dilation then grows dramatically but asymptotically. The closer you move to light speed, the more stretched your time becomes relative to others, approaching stillness but never quite reaching it. The twin paradox imagines one twin traveling at high speed through space while the other remains on Earth. Upon returning, the traveling twin is younger. At first glance, the situation seems symmetrical. Each twin sees the other as moving. So which one ages less? The resolution lies in acceleration. The traveling twin must turn around to return home. That turnaround, the act of accelerating and changing inertial frames, breaks the symmetry. Without that acceleration, both twins could indefinitely claim the other's clock runs slower. But once one twin accelerates, the geometry of space-time assigns different world lines to each. The proper time accumulated along those paths differs. This is not illusion. It has been confirmed in experiments involving precise clocks flown on aircraft. Acceleration marks the divergence. One path through space-time is shorter in proper time than the other, and the clocks quietly record it. In inertial motion, constant velocity, time dilation is symmetrical. If you and I pass each other at high speed, each of us measures the other's clock as running slow. Neither perspective is privileged. Both are correct within their frames. Acceleration changes that balance. When one observer changes velocity, turning around, slowing down, or speeding up, they shift between inertial frames. This frame change alters how simultaneity is defined across space-time. Events that were once considered simultaneous are reassigned. It is this shift that resolves the apparent paradox. The act of turning around is not minor. It reshapes the traveler's path through space-time. Once reunited, the clocks can be directly compared, and the asymmetry becomes measurable. Acceleration is the hinge on which time's symmetry pivots. Here is one of relativity's most subtle truths. If you and I move past one another at 0.9 c, I observe your clock ticking slower than mine. At the same time, you observe my clock ticking slower than yours. Both observations are valid. Neither of us is wrong. This symmetry arises because time dilation depends only on relative velocity. In each inertial frame, the other is moving. The Lorentz transformations preserve consistency. The brain melter quality of this fact comes from our classical intuition, which expects one clock to be truly slower. Relativity replaces that expectation with geometric consistency. The paradox dissolves only when one observer accelerates and the two frames are reunited. Until then, both clocks appear slow from the other's perspective. Two drifting rivers, each seeing the other flow more gently until one curves back to meet the shore. When light climbs out of a gravitational field, it loses energy. This loss appears as an increase in wavelength, a shift toward the red end of the spectrum. This phenomenon is known as gravitational redshift. The connection to time lies in frequency. The frequency of light is directly tied to time intervals. If time flows more slowly deeper in a gravitational well, then light emitted there carries a lower frequency when observed from a region of weaker gravity. The stretching of wavelength reflects the stretching of time. This effect has been measured repeatedly, beginning with the Pound-Rebka experiment. Light itself becomes a messenger of space-time curvature. As it rises, it carries with it the signature of slower time from below, a subtle elongation written into its waves. Black holes represent extreme curvature of space-time. Near their event horizons, gravitational time dilation becomes enormous. To a distant observer, a clock lowered toward a black hole appears to tick more and more slowly as it approaches the horizon. The mathematics of general relativity show that as an object nears the Schwarzschild radius, the gravitational redshift grows without bound. The light emitted from the falling object becomes stretched to longer and longer wavelengths. Eventually, the light fades from detectability, appearing to freeze in time from afar. Yet, to the falling observer, time feels entirely normal. Their heartbeat continues steadily. They cross the horizon without noticing a local singularity. The dramatic slowing is a relational effect, a difference in perspective between frames separated by extreme curvature. From far away, an object falling toward a black hole never seems to fully cross the event horizon. As it approaches, its emitted light becomes increasingly redshifted. The wavelengths stretch toward infinity, the signal weakens, and the object appears to slow to a halt. This is not because the object physically stops. Rather, the time coordinate of the distant observer stretches relative to the falling object's proper time. The light carrying information about the object's motion becomes so red-shifted that it effectively vanishes. The object fades from view. In this sense, the freezing is observational. The geometry of space-time causes signals to stretch and weaken. From the outside, the infalling object seems suspended at the threshold, a silhouette dimming into invisibility. Cross the event horizon, and space-time geometry changes character. In the external region, you can choose to move inward or outward. Inside the horizon, the radial direction toward the singularity becomes time-like. This means that moving toward the center is as inevitable as moving into the future. Just as you cannot stop the passage of time, an object inside the event horizon cannot avoid progressing inward. The coordinate roles of space and time effectively exchange in this region of extreme curvature. This is not metaphor. It is encoded in the metric describing black hole spacetime. The structure of the equations shows that inward motion becomes unavoidable. The geometry itself dictates the path, a quiet, inexorable flow toward the singularity. Neutron stars are remnants of massive stars that have collapsed under gravity, compressing more mass than the Sun into a sphere roughly the size of a city. Their density is extraordinary. A teaspoon of neutron star material would weigh billions of tons on Earth. This immense mass packed into a small radius creates strong space-time curvature. Clocks on the surface of a neutron star tick significantly slower than clocks far away. The gravitational time dilation is measurable in the redshift of light emitted from their surfaces. These stars act as natural laboratories for general relativity. Their intense gravity bends not only light paths, but time itself. In their presence, seconds stretch quietly, shaped by the deep gravitational well surrounding the collapsed core. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep past Earth like cosmic lighthouses, producing extraordinarily regular pulses. Because pulsars are so stable, they function as precise cosmic clocks. In binary systems where two neutron stars orbit each other, their timing reveals subtle relativistic effects. The pulses arrive slightly earlier or later than classical physics would predict, reflecting time dilation and gravitational influences. These timing variations match the predictions of general relativity with remarkable accuracy. Across vast distances, spinning remnants of collapsed stars quietly verify that time bends in gravitational fields. When massive objects like black holes or neutron stars collide, they send ripples through space-time known as gravitational waves. These waves briefly stretch and compress the distances between objects as they pass. Because space-time includes time itself, these waves also involve tiny fluctuations in time intervals. Detectors like LIGO measure incredibly small changes in length, fractions of a proton's diameter, caused by passing waves. These distortions reflect oscillations in space-time geometry. For a fleeting moment, the rhythm of space and time shifts. The universe shivers gently, and instruments record the tremor. Even time participates in these waves, expanding and contracting as space-time ripples outward from distant collisions. At the heart of the Milky Way lies a supermassive black hole known as Sagittarius, a star. Its mass curves space-time strongly in its vicinity. Objects orbiting close to it experience significant gravitational time dilation. Stars that swing near the galactic center move at high velocities and within deep gravitational wells. Their clocks accumulate proper time more slowly compared to clocks far from the center. Observations of these stellar orbits provide further confirmation of relativistic predictions. Even within our own galaxy, time does not flow uniformly. Near the center, seconds stretch subtly under the influence of immense mass. Across the spiral arms where we reside, time moves a little more freely, shaped quietly by the galaxy's vast gravitational architecture. When we observe distant galaxies, we are looking back into earlier eras of the universe. But we are not only seeing ancient light, we are seeing ancient time. The expansion of the universe stretches the wavelengths of light traveling through space, a phenomenon known as cosmological redshift. Along with wavelength, time intervals stretch as well. If a distant supernova explodes billions of light years away, its light reaches us elongated by cosmic expansion. The rise and fall of its brightness unfold more slowly than they would in its own frame. The duration of the event appears extended. This is not due to gravity or velocity in the local sense, but to the expansion of space-time itself. The universe's growth stretches both space and time between distant points. When we observe the deep cosmos, we are witnessing events slowed gently by the widening fabric through which their light travels. Type 1. A supernovae serve as standard candles for measuring cosmic distances. When astronomers study their light curves, the way brightness increases and fades, they notice something precise. Distant supernovae appear to evolve more slowly than nearby ones. The stretching of their light curves matches exactly the factor predicted by cosmological redshift. If a galaxy's light is redshifted by a factor of 2, its time-dependent processes also appear stretched by that same factor. The entire event unfolds more slowly from our perspective. This observation provides strong evidence that the universe is expanding and that time intervals scale with that expansion. Even explosive stellar deaths, unfolding across billions of light years, carry the quiet signature that time itself stretches with the growing cosmos. When light passes near a massive object like a galaxy cluster, its path bends. This effect, called gravitational lensing, is often described spatially. Light curves around mass. But time is involved as well. As light travels through curved space-time, its journey can take longer than it would through flat space. This extra travel time is known as the Shapiro time delay. Signals passing near massive bodies arrive slightly later than expected if gravity were absent. The bending of light is not only a matter of direction, but of duration. Mass reshapes space-time in a way that alters both the route and the time of travel. Even a beam of light racing at the universe's speed limit must follow the contours laid out by gravity. In systems where two neutron stars orbit each other, the gravitational environment is intense. These binary pulses provide one of the most precise tests of general relativity. As the stars orbit, their strong gravitational fields and rapid motion create measurable relativistic effects. The timing of their pulses shifts in ways predicted by gravitational time dilation and orbital decay from gravitational wave emission. The match between observation and theory is extraordinary. Over decades of measurement, the pulses confirm that space-time behaves exactly as Einstein described. Two dense stars circling in silent precision quietly validate the bending of time. Signals sent to spacecraft traveling far from Earth must account for relativistic timing differences. As probes move through varying gravitational fields and at significant speeds, their onboard clocks drift relative to Earth-based clocks. Navigation systems incorporate relativistic corrections to ensure precise communication. Even small mismatches in timing can produce large positional uncertainties across interplanetary distances. When a spacecraft sends data from Mars or beyond, its timing carries the imprint of motion and gravity. Engineers adjust for these shifts continuously. The success of deep space missions depends on acknowledging that time is not uniform across the solar system. Even at the speeds of commercial aircraft, time dilation is measurable with atomic clocks. When clocks are flown around the world and compared to stationary clocks, slight differences emerge. The motion of the aircraft produces velocity time dilation, slowing the airborne clock. However, at cruising altitude, weaker gravity produces gravitational time dilation that slightly speeds it up. The net effect depends on direction and latitude. These differences are minuscule, billionths of a second, yet they align precisely with relativistic predictions. Even ordinary travel reshapes the accumulation of time ever so slightly. Each journey traces a subtly different path through space-time. Shortly after the Big Bang, the universe was denser and hotter than it is today. Under such extreme conditions, space-time curvature was far stronger than in our current cosmic era. Time intervals in those early moments were governed by intense gravitational and energetic conditions. As the universe expanded and cooled, space-time curvature relaxed, and the rate at which large-scale structures evolved changed accordingly. We cannot step into that era directly, but the cosmic microwave background carries echoes of those early conditions. The early universe was a place where density shaped the rhythm of time in ways far more dramatic than we experience now. Galaxy clusters contain enormous amounts of mass, including visible galaxies and vast quantities of dark matter. This mass curves space-time across millions of light-years. Clocks deeper within such gravitational wells tick more slowly than clocks far from the cluster. Light passing through these regions experiences gravitational redshift and time delay effects measurable by astronomers. Across cosmic scales, time flows at slightly different rates depending on gravitational environment. Entire regions of the universe accumulate time differently due to the mass distributed within them, subtle variations woven into large-scale structure. Matter spiraling into black holes forms accretion disks that rotate at high speeds in strong gravitational fields. Both velocity and gravitational time dilation act simultaneously in these environments. As material orbits close to the event horizon, its emitted light shows redshift and timing variations consistent with relativistic predictions. Observations of X-ray emissions from these disks provide evidence for extreme time dilation near black holes. In these regions, space-time curvature becomes pronounced. Time stretches significantly relative to distant observers. The swirling disk glows, shaped not only by heat and motion, but by the deep bending of time itself. Even ordinary stars create measurable gravitational time dilation within their interiors. The center of a massive star lies deeper within its gravitational well than its surface. In principle, a clock at the star's core would tick more slowly than one at its outer layers. While we cannot place clocks inside stars, the equations of general relativity predict this gradient clearly. Gravity does not act uniformly across an object's interior. Time itself varies with depth. Even within a single star, seconds accumulate at slightly different rates, a quiet stratification of time shaped by mass and radius. Although observers in motion relative to one another disagree about how much time passes or how far apart events occur, there is a deeper quantity that remains unchanged. This quantity is called the space-time interval. It combines both the separation in time and the separation in space into one unified geometric measure. In flat space-time, the interval is calculated by taking the negative of the speed of light squared multiplied by the change in time squared, then adding the change in position squared along each spatial direction. Different observers may measure different values for time and distance individually. Yet when those measurements are combined in this specific way, the result remains identical for all inertial observers. This invariance is the hidden symmetry beneath time dilation. Individual clocks may disagree, but the underlying geometry does not. The structure of space-time holds steady, even as its components flex. In 1908, Hermann Minkowski formalized Einstein's insights by describing space-time as a four-dimensional geometric structure. Instead of treating time separately, he showed that space and time form a unified continuum. In this geometry, events are points in space-time, and motion traces world lines. Time dilation emerges naturally from the geometry of these world lines. Just as different paths across a landscape can have different lengths, different paths through space-time accumulate different amounts of proper time. Minkowski space-time reframes relativity as geometry rather than force. Time is not stretched by an external mechanism, it follows from the structure of the continuum itself. Every object traces a path through space-time called a world line. Even when you are sitting still in space, you are moving steadily forward in time, and your world line extends upward along the time dimension. If you move through space, your world line tilts. The greater your velocity, the more your path leans into the spatial dimensions. This tilt corresponds directly to time dilation. The geometry of your path determines how much proper time you accumulate. Two travelers who depart and reunite trace different world lines. The lengths of those paths in space-time differ, and so do their experienced durations. Time becomes a geometric length along your trajectory. In flat space-time, inertial motion, moving at constant velocity without acceleration, maximizes proper time between two events. This may seem counterintuitive, but it is a direct consequence of space-time geometry. In the twin paradox, the twin who remains inertial ages more than the twin who accelerates and changes direction. The accelerated path through space-time is geometrically shorter in proper time. Just as a straight line is the shortest distance between 2 points in space, a straight world line maximizes proper time in flat space-time. Acceleration curves the path and reduces accumulated time. Einstein's equivalence principle states that acceleration and gravity are locally indistinguishable. If you are inside a sealed room, you cannot tell whether the force you feel is due to gravity or acceleration. This equivalence connects velocity time dilation and gravitational time dilation. Acceleration introduces effects similar to those produced by curved spacetime. Both reshape how time flows relative to different observers. The connection reveals a deeper unity. Motion and gravity are not separate phenomena in relativity. They are expressions of spacetime's geometry. In spacetime geometry, light travels along paths where the spacetime interval equals 0. These are called null paths. Because photons move at the invariant speed ccc, they do not experience proper time. From the photon's perspective, though that phrase is limited, no time passes between emission and absorption. This boundary behavior defines the structure of spacetime. Massive objects travel on time-like paths, accumulating proper time. Light defines the limit between what is causally connected and what is not. Relativity preserves causality by limiting signals to speeds at or below light speed. The light cone structure in spacetime diagrams defines which events can influence one another. Events inside your future light cone can be affected by you. Events outside cannot, because no signal can travel faster than light. Time dilation does not violate causality. It reshapes how events relate across frames. The geometry of spacetime protects cause and effect. Even as time stretches and contracts, the structure of light cones maintains order. Although relativity allows time intervals to differ between observers, it does not permit time to run backward for objects moving forward through their world lines. Proper time along a time-like path always increases. You move steadily into the future along your trajectory. Time dilation stretches or compresses intervals relative to others, but it does not reverse their direction. The arrow of time remains intact, grounded in thermodynamics and causality. Relativity modifies duration, not direction. Every massive object shapes the local rate at which time flows. Earth slows time slightly relative to deep space. The Sun slows time more than Earth. Black holes slow it dramatically. These differences are not global distortions but local variations. Each region of spacetime has its own curvature, and therefore its own time rate relative to distant frames. The universe is not governed by a single cosmic clock. Instead, it is a patchwork of locally defined temporal rhythms. In spacetime geometry, every object moves through spacetime at the invariant speed ccc. When you are at rest in space, your motion is directed entirely along the time dimension. As you begin moving through space, some of that motion shifts into spatial directions and less remains in time. This is another way to understand velocity time dilation. Spatial motion reduces temporal accumulation. Even lying still, you are traveling through spacetime at light speed, your motion expressed purely as forward movement in time. When motion becomes rotational rather than purely linear, time dilation still applies. In a rotating system, such as a spinning space station or even the surface of Earth, different points move at different speeds depending on their distance from the center of rotation. The farther from the axis, the greater the tangential velocity. Because velocity time dilation depends on speed, clocks located at larger radii tick slightly more slowly than clocks closer to the axis. On Earth, this means that a clock at the equator, where rotational speed is greatest, accumulates time slightly differently than a clock near the poles. The difference is extremely small, but measurable with precise instruments. Rotation adds another quiet layer to the shaping of time. Even a spinning planet introduces subtle variations in the passage of seconds across its surface. Motion, even gentle and continuous, leaves its imprint on time's steady rhythm. The Sagnac effect occurs when light beams travel in opposite directions around a rotating loop and return at slightly different times. Even though both beams move at the same speed ccc, rotation causes one path to effectively lengthen relative to the other. This effect arises because the platform rotates while the light is in transit. The geometry of spacetime in rotating frames shifts the timing of arrival. Modern ring laser gyroscopes and GPS systems must account for this phenomenon to maintain accuracy. The Sanok effect reminds us that timekeeping is sensitive not only to linear velocity and gravity, but to rotation as well. Space-time does not remain indifferent to circular motion. It responds gently, altering the synchrony of returning light. When a massive object rotates, it does more than curve space-time. It drags it slightly along with its spin. This phenomenon is called frame dragging, predicted by general relativity. Around Earth, this effect is extraordinarily small but measurable. Satellites like Gravity Probe B detected tiny shifts in gyroscope orientations caused by Earth's rotation subtly twisting nearby space-time. In stronger gravitational environments, such as near rapidly spinning black holes, the effect becomes much more pronounced. Frame dragging influences how time and space align near rotating bodies. The very fabric of space-time acquires a faint swirl shaped by angular momentum. Time near a rotating mass is not only slowed, it is gently twisted. A rotating black hole is described by the Kerr metric, a solution to Einstein's field equations that includes angular momentum. Around such an object lies a region called the ergosphere, where space-time is dragged so strongly that nothing can remain stationary relative to distant observers. Inside the ergosphere, all objects must rotate in the direction of the black hole's spin. Time and space coordinates mix in intricate ways, producing stronger and more complex forms of time dilation than in non-rotating cases. The mathematics describing these regions are intricate, yet the physical message is clear. Rotation intensifies space-time distortion. Time stretches not only due to gravity's depth, but also due to space-time's rotational geometry. As gravitational fields deepen, the redshift of emitted light grows more pronounced. This redshift corresponds directly to gravitational time dilation. Light escaping stronger gravity appears increasingly stretched to distant observers. In extreme cases, such as near neutron stars or black holes, the redshift factor becomes substantial. Photons lose energy climbing out of the gravitational well, reflecting the slower passage of time at their point of origin. Gravitational redshift serves as a visible signature of time dilation. By studying spectral lines from distant objects, astronomers can infer how strongly time is being stretched in those regions. Time dilation does not switch on at high speeds or strong gravity. It exists continuously at all velocities and gravitational strengths. The equations of relativity apply universally, even when effects are too small to notice. Every motion, no matter how gentle, introduces a slight adjustment. Every gravitational field, no matter how weak, curves space-time subtly. The fabric does not wait for dramatic conditions to respond. This continuity means that time dilation is not an exotic feature of distant galaxies alone, it is a constant background property of the universe, quietly active everywhere. When two black holes spiral together and merge, the surrounding space-time undergoes dramatic distortion. Gravitational waves radiate outward, carrying information about the changing curvature. During these moments, time near the merging objects experiences rapid and intense variation. Although distant observers detect only subtle ripples, near the event itself, space-time geometry shifts profoundly. The detection of gravitational waves confirms that space-time is dynamic. It responds to motion and mass not only statically but vibrationally, time included. Cosmic rays entering Earth's atmosphere produce cascades of high-energy particles moving at relativistic speeds. These natural experiments occur continuously above us. The extended lifetimes of secondary particles like muons confirm velocity-time dilation repeatedly. No laboratory intervention is required. The atmosphere itself becomes a testing ground for relativistic physics. Even as you rest, particles from distant cosmic events streak overhead, quietly demonstrating that motion reshapes time. Relativity's transformations guarantee that the laws of physics remain identical in all inertial frames. Time dilation is not a distortion added afterward, it is required for consistency. Without time dilation, observers moving relative to one another would disagree about fundamental physical processes. The invariance of physical law demands flexible time and space coordinates. Time dilation preserves coherence. It is not an anomaly, but a safeguard built into space-time's structure. Time dilation operates independently of observers noticing it. It does not depend on awareness or measurement to exist. clocks would still diverge under motion and gravity even if no one compared them. The geometry of space-time governs the accumulation of proper time whether or not it is observed. Time's flexibility is a property of the universe itself, not of perception, not of psychology, but of physical structure. Modern atomic clocks measure time using the vibration frequencies of atoms, often cesium or ytterbium. These vibrations are extraordinarily stable, allowing time to be tracked with accuracy to billionths of a second. Because they are so precise, atomic clocks reveal even the smallest relativistic effects. When identical atomic clocks are placed at different altitudes or set in motion relative to one another, they drift apart exactly as relativity predicts. Raise one clock just a few centimeters higher and it ticks measurably faster due to weaker gravity. Move one at higher speed and it ticks more slowly. These experiments confirm that time dilation is not theoretical abstraction. It is embedded in measurable reality. The quiet oscillations of atoms record space-time's curvature faithfully, turning geometry into observable difference. Coordinated Universal Time, UTC, the global time standard, incorporates relativistic corrections. Satellite-based timekeeping systems adjust continuously for gravitational and velocity time dilation. Without these adjustments, international time coordination would drift, communication systems would misalign, and navigation accuracy would degrade. Relativity is not a fringe consideration, it is operational infrastructure. Every synchronized broadcast, financial timestamp, and navigation signal depends on corrected clocks. Time standards today are not Newtonian. They are relativistic at their core. Gravitational time dilation depends on gravitational potential, not merely gravitational force. It is the depth of the gravitational well that determines how much time slows relative to distant observers. Even in regions where gravitational force is weak, if the potential difference is significant, measurable time dilation occurs. This distinction clarifies why altitude affects clocks even when gravity feels only slightly weaker. Time responds to the geometry of potential, to the curvature accumulated over position. The deeper the well, the slower the clock. In strong gravitational fields, time does not flow uniformly across space. Instead, gradients form. Clocks closer to mass tick more slowly than clocks farther away. These gradients are continuous and smooth. There is no abrupt boundary where time changes rate. The difference accumulates gradually as distance from mass increases. In principle, two clocks placed at slightly different distances from a planet will diverge over time. The effect is subtle but persistent, shaped entirely by space-time curvature. Velocity time dilation and gravitational time dilation can operate simultaneously. In orbiting satellites, for example, velocity slows the clock while weaker gravity speeds it up. The net result depends on which effect dominates. The equations describing these contributions combine within the framework of general relativity. Engineers must compute both to determine accurate timekeeping. Spacetime's geometry is multifaceted. Motion and gravity do not compete. They layer upon one another, shaping the total rate at which time accumulates. In curved spacetime, objects in free fall follow geodesics, the natural, straightest possible paths within curved geometry. Along these paths, proper time is maximized relative to nearby accelerated trajectories. This means that falling freely through gravity accumulates more proper time than resisting gravity through acceleration. The geometry determines the difference. Free fall is not merely motion. It is the natural unfolding of space-time curvature. Time follows these geodesics smoothly. When astronomers observe light from massive stars or compact remnants, they must account for gravitational redshift. The emitted light carries information about how time flows at the source. Measurements of spectral lines reveal shifts consistent with relativistic predictions. These shifts help determine mass, radius, and internal structure. Time dilation thus becomes a diagnostic tool in astrophysics. By observing how time stretches near stars, we infer properties of the stars themselves. As an object approaches a black hole's event horizon, gravitational time dilation increases sharply. From a distant frame, the object's clock appears to slow towards zero. The redshift factor grows without bound, stretching emitted light beyond detection. Yet locally, the falling observer experiences no abrupt halt in time's flow. The contrast between perspectives illustrates relativity's relational nature. Time stretches dramatically across frames while remaining smooth along individual paths. Since its formulation in the early 20th century, relativity has been tested in countless experiments and astronomical observations. Each time, predictions of time dilation have been confirmed. From particle physics to satellite navigation, from pulsar timing to gravitational wave detection, the evidence remains consistent. No credible experiment has overturned relativistic time dilation. Time's flexibility is not speculative. It is repeatedly measured and confirmed across scales. Time dilation does not arise because time is being pushed or pulled. It emerges from geometry, from how space-time is structured. Mass curves space-time. Motion tilts world lines. The accumulation of proper time depends on these geometric features. No external mechanism is required. Time stretches not because it is acted upon, but because it is part of the structure itself. Geometry replaces force as explanation. In relativity, time is not a universal current flowing identically for all observers. Instead, each observer carries their own proper time, the duration measured along their individual world line through space-time. Proper time is not assigned externally. It is accumulated along the path you physically trace from one event to another. It is the time your own clock records as you move. Two observers can begin together and reunite later, yet experience different amounts of proper time between those events. The difference is not illusion or miscalculation. It reflects the geometry of their trajectories. One may have moved at higher velocity. One may have experienced stronger gravitational curvature. Their world lines differ in shape and therefore differ in accumulated temporal length. This reframes time as geometric rather than absolute. Your aging, your duration is bound to the path you follow. Time is not something that happens to you identically everywhere. It is something you accumulate along motion. It is tempting to imagine time dilation as something that only occurs near black holes or at near-light speeds. Yet relativity does not contain thresholds. Its equations apply continuously at every velocity and in every gravitational field, no matter how mild. When you walk across a room, your velocity relative to someone sitting still changes your accumulation of proper time by an amount far too small to perceive, but not zero. When you climb a staircase, the slightly weaker gravitational potential at the top allows your clock to tick marginally faster than one below. These differences are unimaginably small in daily life, yet atomic clocks can detect them. The continuity of relativity is important. Time dilation is not activated only under extreme conditions. It is always present, quietly shaping durations. The fabric of space-time does not turn rigid in gentle environments. It remains flexible everywhere, even when the stretching is subtle beyond perception. At the core of special relativity lies a single uncompromising constraint. The speed of light in vacuum CCC must be measured identically by all observers in inertial motion. This invariance is not negotiable. It emerges from Maxwell's equations and has been confirmed experimentally with extraordinary precision. If time were absolute and identical in all frames, observers moving relative to one another would measure different light speeds. To prevent this contradiction, space-time must adjust. Durations stretch, lengths contract. The coordinates of space and time transform in such a way that CCC remains fixed. Time becomes a flexible variable, not because of philosophical reinterpretation, but because geometry demands it. Time dilation is therefore not a distortion imposed arbitrarily. It is a structural necessity. The universe preserves the constancy of light by allowing time itself to adjust. The flexibility of time protects the deeper symmetry of space-time. Before Einstein, time was treated as a universal parameter, ticking identically for all observers. Newtonian mechanics assumed a shared cosmic clock. Relativity dissolved this assumption and replaced it with relational time, time measured relative to a frame of reference. Two observers moving relative to one another can measure different durations between the same pair of events. Neither measurement is privileged. Each is valid within its own frame. The laws of physics remain identical, but the decomposition of space-time into space and time differs. This shift is not chaotic. It is deeply ordered. Relativity provides exact transformation equations that connect frames. Time becomes frame-dependent, yet mathematically precise. Instead of a single universal now, we have consistent local times defined by motion and gravity. The universe does not lose coherence, it gains geometric structure. The strength of gravitational time dilation depends on how deeply space-time is curved by mass. When mass is compressed into a smaller radius, curvature increases dramatically. Neutron stars and black holes represent extreme examples of this concentration. Near such compact objects, clocks tick far more slowly relative to distant observers. Light emitted from their surfaces carries measurable gravitational redshift, revealing the stretching of time at the source. The deeper the gravitational well, the greater the dilation factor. These objects allow physicists to test general relativity in strong field conditions. Observations match theoretical predictions closely. Time near compact masses does not behave differently in principle. It simply stretches more profoundly due to curvature. The geometry grows steeper and time follows its slope. Einstein's equivalence principle states that locally, the effects of acceleration and gravity are indistinguishable. If you are inside a sealed elevator accelerating upward, the force you feel is equivalent to gravitational pull. Conversely, standing in a gravitational field is locally equivalent to being in an accelerating frame. This equivalence explains why acceleration influences time similarly to gravity. In an accelerating spacecraft, clocks positioned at different heights tick at different rates, mirroring gravitational time dilation. The mathematics describing these differences align with the equations of curved spacetime. Acceleration and gravity are not separate phenomena within relativity. They are two manifestations of spacetime geometry. Time responds similarly to both because both reshape the structure in which clocks operate. Relativistic time dilation does not selectively slow mechanical clocks while leaving biological processes unchanged. It applies uniformly to all physical phenomena governed by space-time. Chemical reactions, radioactive decay, neural activity, and atomic oscillations all follow the same temporal scaling within a given frame. If your proper time accumulates more slowly relative to another observer, every process in your body slows proportionally from that observer's perspective. There is no hidden exception. Time dilation is comprehensive. This universality preserves internal consistency. Physics does not fragment under relativity. All processes remain synchronized within their local frame. The slowing or speeding of time affects everything equally, maintaining coherence along each world line. In relativity, duration is not assigned externally by a universal clock. It arises from geometry. The amount of time that passes between two events depends on the path taken through space-time. This path-dependent duration is called proper time. In flat space-time, the interval between events is determined by combining time separation and spatial separation in a precise way. One calculates the negative of the speed of light squared multiplied by the change in time squared, and then adds the square of the distance traveled through space. For objects moving slower than light, this combined quantity defines how much proper time accumulates along their path. Different observers may describe the same events with different splits between space and time. Yet the geometric interval remains consistent. Duration is therefore not an external backdrop. It is built directly into the structure of space-time itself. Space-time diagrams include light cones, structures that define the limits of causal influence. Events inside your future light cone can be affected by you. Events outside cannot, because no signal travels faster than light. Time dilation does not disrupt this causal order. Even when observers disagree about durations or simultaneity, the light cone structure ensures that cause precedes effect within each frame. The preservation of causality is one of relativity's deepest consistencies. Time may stretch and contract, but the ordering of events remains protected by space-time geometry. Relativity modifies how long intervals last between frames, but it does not reverse the direction of proper time. Along any time-like world line, proper time increases steadily. The thermodynamic arrow of time, governed by entropy, remains intact. Causes precede effects. Processes unfold forward. Time dilation adjusts the rate at which duration accumulates, not its orientation. Even in extreme relativistic conditions, objects continue moving into their future. Time's direction remains anchored, while its pace adapts to motion and gravity. It is natural to imagine that somewhere, perhaps woven into the fabric of the universe, there exists a master clock ticking identically for all observers. Relativity removes this idea entirely. There is no global cosmic time that flows uniformly everywhere. Instead, time is defined locally within regions of space-time and along individual world lines. In cosmology, scientists sometimes refer to cosmic time, but even this is a coordinate choice tied to the large-scale expansion of the universe. It does not override local relativistic effects. In regions of strong gravity or high velocity, clocks still diverge from that cosmological reference. There is no absolute temporal authority governing every event simultaneously. The universe operates without a single shared metronome. Each observer carries their own ticking rhythm, shaped by motion and gravity. Time is not centralized. It is distributed, geometric, and locally defined across the vast structure of space-time. In everyday life, the present feels universal. Yet in relativity, what counts as now depends on your state of motion. Two observers moving relative to one another can disagree about whether distant events are simultaneous. This is known as the relativity of simultaneity. When one observer changes velocity, their slicing of space-time into past, present, and future tilts. Events that were once considered simultaneous may shift into different temporal orderings. This effect is not philosophical speculation. It arises directly from Lorentz transformations. The present moment, therefore, is not a global surface stretching uniformly across the cosmos. It is local to your frame. Your now is defined by your motion. Time's division into moments depends on how you move through space-time. If humans were able to travel at velocities close to the speed of light, time dilation would have profound consequences for lifespan comparison. A traveler moving at relativistic speeds could return having aged far less than those who remained behind. The mathematics are straightforward. As velocity approaches CCC, the Lorentz factor grows, stretching coordinate time relative to proper time. Months for the traveler could correspond to years or decades for observers at rest. This is not fictional exaggeration. It is a direct outcome of space-time geometry. Motion changes duration. Long voyages through space would also become voyages through differing accumulations of time. Earth moves around the Sun at approximately 30 kilometers per second. This orbital velocity introduces a tiny but real velocity time dilation relative to an observer at rest with respect to the Sun. Additionally, Earth sits within the Sun's gravitational field, which also affects the rate at which clocks tick compared to deep interstellar space. Both motion and gravity influence the proper time accumulated on our planet. These effects are small but continuous. Every second you experience is shaped not only by Earth's gravity but by its motion through the solar system. Your world line is not stationary in the cosmos. It traces a gentle curve around a star. Spacecraft traveling to other planets experience varying gravitational fields and velocities during their journeys. Engineers must account for relativistic time dilation when calculating communication delays and trajectory corrections. As a probe approaches a planet, gravitational time dilation increases slightly. As it accelerates, velocity time dilation contributes additional adjustments. Though small, these corrections ensure precise navigation. Timekeeping in space exploration is inherently relativistic. Every mission relies on understanding how space-time geometry affects clocks beyond Earth. Relativity reveals that time is not a separate backdrop against which events unfold. It is a dimension woven inseparably with space. Together they form space-time, the arena in which all physical processes occur. The metric that describes this structure combines spatial and temporal components into a unified expression. Time is not external to geometry, it is part of it. When space-time curves, time curves with it. When motion tilts a world line, time adjusts accordingly. Reality is not staged upon time. Reality includes time as part of its structure. Physicists often summarize the geometry of flat space-time in a compact mathematical statement. In spoken form, it says this: The space-time interval equals the negative of the speed of light squared multiplied by the change in time squared, plus the square of the change in position in each spatial direction. This expression encodes the inseparability of space and time. The negative sign attached to the time component distinguishes it from spatial dimensions while preserving unity within one framework. Observers moving relative to one another may measure different durations and distances, but when those quantities are combined according to this rule, the result remains unchanged. This single geometric relationship explains why time dilates and lengths contract. It is not an added correction, it is a natural outcome of space-time structure. Your life can be represented as a continuous world line through space-time. The length of that world line in the temporal sense corresponds to your proper time. Different paths between the same events can accumulate different durations. Acceleration, velocity, and gravitational environment all shape the curve of that path. Time is therefore path-dependent. The geometry of your motion determines the duration you experience. Even when you feel still, you are moving through space-time. In the absence of spatial motion, your trajectory lies entirely along the time dimension. As you move through space, part of that motion shifts from time into space, resulting in velocity-time dilation. The total space-time speed remains constant at CCC, expressed differently depending on your motion. You are never stationary in space-time. Your world line extends forward continuously, shaped by motion and gravity. Time does not sit outside the universe, ticking independently of events. It responds to motion and mass. It stretches in gravitational wells. It contracts under velocity transformations. Relativity replaces rigid background time with dynamic geometric time. The passage of seconds depends on space-time curvature and world line shape. Time is flexible, structured, and measurable, but not absolute. At the deepest level described by relativity, time is not separate from space. It is woven into the same fabric. The geometry that governs the universe can be expressed through the relationship between time intervals and spatial intervals, a relationship that combines the speed of light with changes in time and position into one unified measure. When mass is present, that geometry curves. When motion increases, world lines tilt. Proper time accumulates according to the shape of those curves. Duration is not imposed externally. It is determined by how you move through the structure itself. Time is therefore not a rigid stage on which events unfold. It is part of the architecture. As you rest, you are moving through that geometry, accumulating your own proper time along a quiet path through curved space-time. Now let your breathing settle again. You are not outside time, watching it pass. You are inside it, moving through curved space-time at this very moment. Earth's gravity shapes your seconds. Earth's motion around the sun shapes them too. Even as you lie still, your world line extends gently forward. Time is not racing. It is unfolding according to the geometry that surrounds you. The universe is not ticking against you, it is carrying you. So rest here inside this quiet structure. Let the vastness hold you, and allow your own proper time to continue, softly, into sleep.